Good day everyone. I am Sumudu Samarakoon, an Assistant Professor from Center for Wireless Communication in University of Oulu and a member of Intelligent Connectivity Group. Along with this month's topics of 6G talks, I would like to present under the title Communication Control Co-Design from Research to Applications. During this presentation, first, I will discuss about next generation of IoT networks and introduce wireless network control systems. Then, I will provide an overview on different scales of wireless network control systems. Afterwards, I will briefly discuss about some of communication control co-design enablers and our ongoing demos. Next generation of IoT networks consists of various types of applications providing different services with many devices. The services vary from simple repetitive tasks to complex mission-critical ones. They have common requirements in terms of reliable connectivity, robust autonomy with guaranteed privacy and security, which need to be scaled as the network scales. Hence, the recent interest is to move from cloud-centric design to cloud-assisted or distributed design, where the decision-making capabilities are moving towards the edge. One of the common subsystems of the IoT networks is control systems. Control systems consist of sensors, controllers, and actuators that interact with the environment. Sensors obtain states of the environment with possible defects and feed them to the controller. Based on the application requirements, the controller makes control decisions. These decisions drive actuators and impose changes on the environment, in which state of the environment updates. The design of control system relies on some requirements such as ensuring the ability to infer the states from sensing signals and ability to control towards maintaining the stability of the system. The control theory offers various techniques to analyze complex dynamic systems, how to simplify them to provide practicable control solutions. Consider the scenario where either one or both sensing and controlling links are wireless links. As such, the sensors, controllers, and actuators are likely to be deployed in physically separated locations. These are referred to as wireless networked control systems. Here, the communication between network elements are going to play a major role in the overall performance of the system. The communicate sensory and control information are subject to noises, losses, and delays due to the stochastic nature of the wireless channels and the availability of limited communication resources. Hence, fulfilling the control requirements is going to be more challenging in wireless network control systems. However, we can resort to the tools and techniques offered by the communication theory. Ensuring reliable communication with low latency conditions under limited connectivity and wireless resources is one of the prime goals of wireless communication network design. Instead of defining control and communication requirements separately, assuming an independence, now it is vital to consider solutions that account for the joint design of control and communication. Further, I would like to highlight some pivotal points. The complex environments are with both known and unknown variables that define their characteristics. Moreover, the changes in the environments are related to the changes of these variables. Knowing how these variables work together, what causes which, why there are certain behaviors, is essential to clearly understand the underlying true dynamics of the environment. Another remark is that what the sensors observe and what is the actual state of the environment could not be identical. Either sensors are limited to observe a partial state of the environment, or the observations are merely high dimensional reflects that correlate with the underlying causal behavior of the system. Hence, relying on sensing and monitoring data in their raw form for decision making might not be the ideal way to control the control system. Furthermore, there could be temporal changes in the sensing and actuation components. Their modalities or characteristics could be drifting, in which affecting how accurate the environment is perceived and interact with it. In some cases, new components are introduced or existing ones are removed from the system, and thus the decision making needs to be adapted accordingly. Finally, it is essential to highlight that both the communication and control need to be goal-oriented. By that, we need to ask the question, do we need to have the transmitter-receiver design to accurately obtain sensing information and deliver control decisions? Or do we just need to design a flow of operation that allows to complete our goal? Towards these goals, we need to resort to the tools from machine learning. Due to the data-driven nature, machine learning tools can learn the requirements and goals of both control and communication and can help to infer the decision. Machine learning brings the capabilities of online and offline learning, which are useful to adapt to different application requirements and dynamics of network conditions. In addition, machine learning can be used to replace the complex computation and to learn informative representations that are needed for optimization. These models rely on algebraic equation computations, which are specifically useful for constrained devices. In this view, the analysis of wireless network control systems can be seen as confluence of control theory, communication theory, and machine learning. We can look at different types of wireless network control systems at different scales. With a single decision maker or an agent, control systems could be controlling a single plant having one or many sensors and actuators focusing on a specific task. An example could be remote control drone. The visual signals are needed at the controller to make the decision that are then used to control the propellers in real time. The delays, errors, and losses in communication and control decisions directly impact how well the drone could fly smoothly. If we scale the system with multiple sensor actuator units assigned for different tasks, but still controlled by a single agent, we have a different scenario. For an example, it could be a manufacturing plant, possibly operated in a semi-autonomous manner by a centralized central control unit. Instead, we can consider a system focusing on one task, but controlling is carried by multiple individuals. For an example, a telesurgery scenario where multiple surgeons operating a patient in a collaborative manner. Here, all agents share the perspective and possibly share the resources as well. Finally, we can have systems with multiple control units acting together. Remotely controlled vehicles along autonomous and conventional ones could be one such scenario. Here, agents have partial view of the states, limited resources to communicate, yet still need to make decisions that affect either all or many of others. Each of these scenarios introduce different challenges of enabling application-specific requirements. Hence, it is essential to seek for various mathematical concepts to develop accurate and efficient analytical models of these systems and their operations. These models can be used to design centralized and distributed decision makers. The quality of the solutions relies on how well we identify underlying semantics of the tasks. Then again, for practical applications, it is vital to have generalized designs as well. Towards achieving these goals, I would like to highlight few enablers. First, we have to handle the tail distributions corresponding to the rare situations. In certain critical applications, this is something that needs to be handled mostly without experience in them. Here, we need to seek for analytical tools or data-driven designs such as extreme value theory and survival analysis to model these situations and react before they occur. Another aspect is to develop designs that improve the worst case performance. The distributed robust optimization is useful to handle data heterogeneity over different distributions and environments. Human expertise can be used continuously within the autonomous systems whenever they fail to act in the desirable manner. With the tools of supervised and reinforcement learning, we can develop knowledge and skill transfer from humans to machines. It is important to focus on the causality and invariance to have robust designs. Here, invariant risk minimization and representation learning techniques are needed to abstract the important information from the observations that are possibly static over the changes of the environment. Using such latent information to communicate, to control, or to infer can improve the robustness of the solutions. Under predictive control techniques, we rely on reinforcement learning and Bayesian learning methods to learn and infer sensing and controlling information, which reduces the burden of communication. For large-scale networks, we can exploit hardening effects as per mean field and random matrix theories to simplify the complex interactions. Another concept is to discover semantics and new communication protocols that are based on objectives of the task at hand. As different network entities sense and interact based on their objective, such acts can lead to emerge new protocols in terms of what to do, when to do, and how to do, rather than following a set of protocols that are handcrafted without focusing the specific goal of the task. Towards the validation of this line of research, we are currently working on several demos. One of them is focused on causal discovery from pixels, which is used for the control. Learning the dynamics in a latent space allows accurate decision making, efficient modeling of the system, and reducing the communication payload. We intend to validate this on a classical card pole setting as well as with a VR-based remote control scenario. Another work focuses on learning a protocol for controlling. Accounting for the control requirements, here we design learning protocol that is focused on jointly design the codebook and compute the communication frequency. The edge-assisted navigation and obstacle bypassing robot design is another demo. Here, the edge identifies the goals specified by human operators. The robot is in the contact with the edge, uses an onboard path following model as well as an obstacle bypassing model that imitates the decision of an expert. The federated learning for maze discovery demonstrates the collaborative learning of multiple robots. Here, the robots learn to map sensory data to the structure of different sections of the maze. To improve the learning process, we use a simulated environment to select the neural network architecture and pre-training the machine learning model and then transfer that knowledge to the actual setup. With this, I would like to conclude my presentation. Thank you.